small figures, the inside figures of the graph, which is 1 to 3 days, and others are 1 to 28 days. Now, looking at this RMSD we take the baseline signature, which is to be intact as a day 1, because this is the baseline from the day 1 after the molding or casting, and we compare the same signature from the day 1 signature and do this RMSD variation. RMSD what we call the root mean square variation of signals, because here we are talking for signals, so we use that one of the damage metric to understand. But here damage is strain development, not damage, other real cells. Now, if you see the changes, okay, for surface content there is a rampant. For everyday form, after day 10, the variation is not too much, but there is a changes are within 10%, day 14 to day 28. But if you see the metal wire vest, there is no such pattern I can induce from this particular graph. Now, what else gives me an idea? Change in any indices is completely vibrant. It's ambiguity. It doesn't have any decision based on this particular changes. Now, what else we do? We do some kind of inverse method. What exactly the inverse method do we do? You have a signal. This is the signal. It has a signature. And the signature, we also plot the conductance to give the information in terms of structural information. Now, susceptance also there, which is not being used. And we want the conductance susceptance to be reverse engineered and do some kind of identified mass, spring, and damper system. What exactly I did? I took a signal and I reprocessed it in terms of Hickson model, where in Hickson model it has a lot of spring mass damper combinations are there, and each of this combination you have a certain pattern. So if you see, this is the certain pattern certain pattern we must see over there. So it is just be because of flip flop, it should be X and this should be Y. Just flip flop. This X can be positive, it can't be negative. So this is X is completely positive, Y is it has a negative and positive Y. So what I did, I plot my certain range of frequency from the signature and try to map with which combination of spring mass damper system it works. Okay, what is the signature you have? 30 to 300 kilohertz. It has a lot of curves, very fixed, and we need to think why you choose 170 to 190. You can take 50 to 100, you can take 120 to 170, or anything you like, somebody is free to do. So, what is the inverse engineering method we usually follow? In vibration, your structure has input which has been considered as in terms of signal. Now, the signal has the basic property of structure, which is called mass, strain, and dampness, MCK, which is we do in a model operating or global vibration method. We can understand structural vibration. Any of you had the structural vibration as a course? Structural vibration, structural dynamics, right? So we know how to solve the Eisenhower problem. Then model matrices, right? Model matrices of MCK, right? Drum masses, all these things we know, right? So that part is now called forward engineering. आपके पास सिस्टम है, आपने सिग्नल लिया, सिग्नल मेजर किया, उससे आपने सिग्नल को एक फॉर्म मैथमेटिकली सॉल्व किया, and you got something. That is called forward engineering. But now inverse engineering is you don't only say, you don't know what is what. कहाँ से आया, किधर आया, किस सिग्नल आपने पता. फिर हमको क्या करना है? We have to do a regression analysis. So each of the signature has from 30 to 300 to fragment it up. And each of the fragment will be weighted with a certain kind of weight factor, A0, A1, A2, A3, up to AN. Now, when these weight factors now combined with a different form of regression formula, then we call this approximated method or inverse engineering. The one which is I am explaining in Hickson model is about one of inverse engineering, but where we see the pattern. भाई तुमने एक सेक्शन लिया, उसकी पैटर्न कहाँ पे फिट हो रहा है? कोई मास स्प्रिंग एंड डैम्पर सिस्टम में कहीं फिट हो रहा है क्या? तो मैंने 170 से 180 वाला एक सेक्शन लिया एंड वी ट्राई टू फिक्स आउट कि भाई ये कौन सा मॉडल पे फिट हो रहा है. किया तो देखा मेरा ये वाली combination fit हो रहा है. Now this combination has a certain information about the x and y that is called should be dependent on MCK. These are expressions are mass spring damper system. So what we have now, we have a pattern which is to match with the experimental data which is we as a signature, and also we try to fit in this model that is happening here. So here this is just interchanged. Now what we have value, we can get number of x and y and value from 170 to 180. Then each of having a lot of simultaneous equations solving of it, we can easily calculate AMCK taking the frequency as constant. So what I told you, x and omega is known for us. If you see these two equations, x and y with the depends on MCK and omega. So from this two curve, can I have a multiple x, x0, x1, x2, y0, y1, y2 with a similar, with the corresponding frequency omega 0, omega 1, omega 2? Can I have a lot of equations, solve it and get me the MCK value for a particular range? And this gives you the result-based strong spring mass damper system to understand what kind of dynamic model it is. With this thought, there I didn't calculate all, I only included the stiffness measurement, because how we calculate stiffness? I use this particular formula. Y has K, does the Y has K, right? So I have a Y in this particular, take this particular curve, can have a Y0, Y1, Y2, Y3, I can have corresponding omega 0, omega 2, omega 3 as a frequency, solve it out and find out my K. Now, I did it from not only day 1 signature, day 1 to day 2 date signature, and find the K variation that is called piezo identified Hexagon based stiffness to be calculated from all the 3 samples for the metal wire applications. Why I didn't show this conventional or the embedded form? There's many of the researcher or my research groups in IIT Delhi already covered. So I just only put it the metal wire based application, because these are as much as compared to the conventional method which is already done by the other researchers. So I didn't add it. But I simply wanted to say here, the stiffness measured through the Gibson model being plotted over the 20 days of hydration, either in a short form that is from 1 to 14 hours, that is the day 2 days hydration for short term, or long term hydration, the change is happening. Looking at the behavior, why I should talk about concrete, corresponding to how it is hydrated, we just said through solution hydration, and there is a solid state hydration. Now the first 3 days are very much responsible for early strength and high heat of hydration as well as setting time. So all you see, there is a large increase of the stiffness values. But later on, till 3rd to 7 days, there is called stagnation phase. Stagnation phase is the stagnation phase where you got solid state of hydration. The water is super saturated, you don't have any water to react to cement particle. The saturations already happen. All you have the crystallized compound, they do react itself form the strength compound, which is saying that after 7 days there is a kind of stagnation or the plateau in the curve, shows that the strength development is very slow and steady, and it attains almost a constant plateau value till 28 days. This gives you also idea that the C3A are early to behave, but C2S is the late to react and gives the final ultimate strength in the compound. So this is where I mentioned only for the metal wire, but others are already being seen, and you can look at it, you can research paper to it. So I hope you understand this part beautifully. Shall I bit? Anything you can refer the paper. Now, okay, don't tell me what to do. Just give me a one simple part. What should be a take-home message to an engineer? So when it has a lot of times we did it, we do some kind of parametric variation, parametric ratio over the 28 days variation. So if you see, after day 7 or day 8, for all 3 specimens, if you consider the day 0.4, this is called parametric ratio, we consider it as a 0.4, which when it is reached to that parametric ratio, we understand the concrete is almost given strength. So if you look at K or having a similar attain similar delta K by K parametric value or ratio all together for all the three specimens for a longer period of time. Now, if you see the green arm are picked up on and off, because the day 3, the specimen 3 has a lot of shrinkage track. So, initial days, it has a rapid changes, but the later stage, the day 22, 24, 26, it do suddenly, it do perform very well. How does it happen? Concrete has autogeneous healing, because the lime is there, and lime is a breathable element. Whenever it got CO2 and moisture from this, it automatically react and form the cementitious one. So autogeneous healing is already there. So that is what specimen 3 doesn't well behave well, but from day 21 onwards do perform better towards the sensor diagnosis. The first one, why I just talk about, my research is not part to understand this non-bonded configuration, that is metal fibers has potential to have any kind of SHM EMI based SHM technique or not. So first we understand we do it for hydration monitoring, and it is very much required when the accessibility to the structural part is restricted or prohibited. And with the RMST signatures or the conductance behavior, we understand that picture covered signatures are good enough to dictate changes through the metal-wise configurations, because it do reflect the physiochemical changes by physiochemical parameters as well. And what we understand, though it's a non-attached configuration, if the thin the metal foil, the more better is the surface wave propagation and interact with the structure to keep effective behavioral change of the complexity of the hydration process. So this is the one of the part which I did cover during my one of my research student has worked out. Then later on we response this one of the PhD students' work is about how does the bond in the concrete also behave. Now when the reinforcement embedded into a concrete, it has a adhesion. It has a chemical adhesion, mechanical interlocking because of the undulation between each of the steel's reinforcement and their shear bond configuration during the hydration development. Now, when they break, there are two type break. We call flexural bond, but with an anchorage bond. So most of the part we are dealing now in this particular research, we are dealing on the pull-out test, which is called anchorage behavior. Now, when you have the anchorage behavior and the bond do fail due to the tensile pull, how does the crack appear? Maximum crack that will appear near about the concrete surrounding the steel bar. These are the steel bar. Now, concrete surrounding the steel bar got crushed first. Okay. It depends on a very simple. No. It depends on the grade of concrete, grade of steel, and how much force you apply for. Now, let's say concrete is completely mature, and you have a steel, and the steel has a pull-out test. Let's say you have a maximum pull, and the steel is come out. Now, concrete, how the concrete will fail? First of all, it crushed as a locally. Then once the concrete, the crust and the steel has a higher grade, like let's say Fe 4.5 or Fe 500, the larger is the dia and the higher strength steel, then we try to cross it first, the concrete surrounding the steel, and then further propagate as a gradient. So we call it's called split tensile strength, split tensile test or split decoration, splitting of the concrete. We see once the concrete crust and it is radiated completely as a behavior as a failure. Now I'll show you the picture. If you see this method of development, strength development and the bond diffusion is very global is a splitting, local is a crushing, and to understand the behavior, you need a bit of monitoring methods. There are thousands methods are available. People do in a conventional way, acoustic emission way, local eco-pulse way. So, but many of the work has not done with the first of all in the piezoelectric sensor based. So, first thing, what is the challenge? It is challenge I will show you. But another important to understand the slip. So, there is a relative displacement between this concrete surrounding concrete and the steel while it is being pulled is called slip. And what exactly the slip displacement in terms of mm, and at what load the slip occurs is very important to know, because that gives you the interfacial strength measurement, which is never been known in a condition. Because nobody know, हमको स्ट्रेंथ पता है कंक्रीट का, हमें स्ट्रेंथ पता है स्टील का, हम मैक्सिमम हम जब उसको पुल आउट टेस्ट करते हैं हमें क्या आता है, टाउ डिग्री बॉन्ड स्ट्रेंथ हम निकालते हैं आरसीसी में, isn't it? So that is maximum we know, and हमने कोड में देखी है, that's enough, we don't care about it. But actually how does the concrete compacted, if it is a not self compacted concrete, if it is a honeycombing, if there is a lot of work, we do not know how the concrete and steel is bonded together, right? So to understand this behavior, we use the piezoelectric sensors for the monitoring. Okay. Then what are the next challenges? The next challenge is more about how to utilize it. Because the steel is curved fast, right? Steel bar is curveless. It has an undulation, right? It has a ribbed surfaces. PJT कहाँ लगाएगा? ये तो flat surface है. तो हम how we should attach the sensors? Sensors need a place to attach it. So again, this is one of the major things. So we'll go by one. So what is the strength that I told you? The steel has a ribs as well as some adjacent friction, which allow the concrete to crust. But if you have a more load with a large grade of steel, then the cracks rapidly grow in a radial manner, which is called splitting crack. Now the splitting crack is very dangerous, because with a small force of action, it do allow the concrete cover to go. So when the concrete cover is gone, what happens? Steel is exposed to the environment. Then what happens? Rust, corrosion, some more dangerous structural capacity to be gone. So I am not explaining this. I think I am running late. Okay. Now, what is we talk about? The bond stress or bond strength, which is depend in our coder book. What it says, based on the grade of steel and the grade of concrete, we choose. First of all, grade of concrete से एक value आ जाता है. With based on the changing high strength AICTE bar, we increase 20%, 60%, whatever, right? That is what we do in assessing that. But it is the where the failure is done. That is what. But we understand now how the frictional or chemical addition has some kind of interaction force that is being developed or not. First thing. Second thing, at what point the slip occurs. Once the slip occurs, the steel, concrete surrounding the steel, it got crushed. Then let it cross, then it will propagate gradually so that it can make a large crack, so that cover to be out. And having said that, this particular splitting and the cover to out is dangerous. Now, if you look at this different changes in the slip versus stress, this is called slip versus the shear stress. Now, if you see the deformed bar, the HISD bar and the normal steel bar, and the rounded MS steel bar has a very different form of curve when we talk about stress versus slip, and this deformations always being noticed in terms of higher maximum stress and a longer slip. Now, this has a longer slip, almost the same, but the next still has a longer slip. Slip means these are well deformations or slip that measure from steel to concrete. The steel has to be deformed and the concrete surrounding also be crushed. So the relative displacement to be measured as per slip. Larger is the slip, better is the resistance to the bond failure. Now, what are the things we do in the infection? If you look at how it has been measured throughout the history, if you see the three factors I said, chemical addition, mechanical interlocking and some friction, but maximum we have two kind of test method, which is a fractional test. One is called pull-out test, where the steel, concrete and the steel has been completely embedded into the form, and we try to pull the steel either top from the top, and we have a LDPT, we have two at the top and bottom, and we calculate the relative displacement of the steel and concrete through this mechanical loading and calculate the slip. Now, mostly of the important parameters are their concrete strength, which then a concrete use, how much concrete cover to be provided, what is the diameter of steel bar, what is the grade of steel bar, their casting methods, aggregate is properly packed or joining is not there or not. All of the things are being mentioned. So my work, and there is a flexural test also we do with the based on the beam bending, but that is not what we are. My work is based on. I did it in the pull-out test. So why we did this first of all monitoring? Because normal beam bending testing and all this pull-out testing had a destructive nature, time consuming, has a lab hour to know about it, and it is not much of too economical because you are destructive the tension, or you take a core out of it and do some test to be done, which is not good enough to make a repetitive to do. So we should do a bit of SHM on this part. So I'm just making this mistake of this. I'm going back to again this test. So I've skipped two of this because we just deal on steel bar. So let's talk about the beam cylinders embedded in the steel. So we have to have this bond strength monitoring. We have this three form of the concrete specimens, which is still is completely embedded into whole length, and the three form of PZT patch has been instrumented. One is we get a bit of mass loss within the steel surface and allow the PZT patch to bond it with the flattening, by flattening them into the polishing into the steel bar. Other one which we do using the duplicate, which is called cloud based. What you see in the red is a thin aluminum foil. PZT is bonded to it, and the duplicates are the two ends of the thin film now being tightened with a screw tight. Now other part which you just like the metal wire based test or metal wire based video sensors, which is attached to the one of the end of the PZT patch, which is stay outside the steel bar itself, no concrete attachment to them. Each are 102 by 200 and concrete cylinders, 16 mm HYSD bar being used for this particular test. And this is the casting what we do, and we do it for lactobacillus test curing. All the sensors are being well equipped and being well instrumented, soldered, being well capped with the adhesives, and the sensors are kept bit outside or well packaged so that it should not be rust during this. Okay, and all the mixed design, all cloud test has been accorded with the European standard or some AICTE standard for this one. And later we do test. The first one that we did, we also try to let's to understand how does the interlocking or chemical adhesion initiate. So we did it for 1 month, 28 days. We did every day's hydration monitoring for the bond strength, because the bond strength also need to happen. Then only we do the pull-out test. So we did it for some signatures while for monitoring for first 28 days. Then we also did it for the full specimen pull-out test while being utilized in a UK. So okay, so we have not mentioned forget to put the so what we do over here, you see we have a two attachment of the steel plate attachment. I have two screw threaded changes to the plates at the two end. Now the pulled specimens are being stationed in the middle, and the sensor wires are being integrated with the LCR meter, and we also have LVDT attached to the top of the top plate of this pull-out specimen arrangement, and we apply the tensile pull. So with the application of tensile pull, the steel bar will come out, and we measure the slip from the LDVT, as well as we got SR meter width. So as it is for stress control UTM, so what we do for strain based control UTM, so we for every displacement level, we for 10 mm, 120 mm, 30 mm, every 10 mm displacement interval, we take the measurements, and with the measurements we also get the signatures from the LCR meter. So this signatures are now, these are the stress versus slip curve for the the concrete specimen which is being shown, and these are the properties which is being used for the concrete to be casted with all metal property of the aggregate sand cement. And if you see the specimens comes around the compressive strength has been achieved because we did it for 830 concrete for this for 3 specimens. But if you see the overall crack displacement, what we got is the slip stress versus slip curve. 3 elastic pro what is we call pro peak post peak pre peak behavior is very seen in our machine, but post peak behavior is mostly contained. So because as a strain control and it is much not into a very well good to after the break up, after the concrete steel is pulled out, the machine is suddenly stopped. So the post peak behavior is much not being investigated, but pre peak behavior we got a large enough elastic strength which is good for to be shown or utilized to understand the behavior of the specimens for bond strength. So how it happens? You have a specimen on crack version, then you when you pulling action that happen, you have a crushing of the concrete surrounding of the surrounding concrete, then the crack radially propagate and the overly split into abs. And this is the very much common pattern what we see in our stage. So this is the spectrum which is the elastic hydration changes or what you the hydration, how the strain development happens, all the 3 forms of jelly attachment, and all you see the peaks are shifting right where the strain development happens, as well as there is a change in the peaks for the metal wire clamp and the surface content being seen. For clamp is very nicely being seen the changes to the bond strength development interface, and metal wires not much variation being shown, but if you go quickly, yes, there is a significant change within the signatures that have been taken for strength development. The same thing which we see as a statistical variation, but the statistical variation changes for strength development for bonded. First 2 things are very, first 2 PGT is very simple and is so direct enhancement, but it doesn't for the cloud metal based, it has a very random pictures. So we try to segregate that part. Now what we see here, again the Higson model, we use the piezo equivalent mass stiffness. We see there is a change in stiffness value or increasing trend of stiffness value because the hydration allows the strength to develop, and this gives this good chemical adhesion and mechanical interlocking that is to be monitored during this 28 days of cure. And the last part what we did with the strain control mechanism, we allowed to do the pull-out test, and of the different pull-out test in action. If you see the variation, as it is very difficult to do all the 4 to 5 variant, and with the certain putting them to a stack and allow to pause for 2 to 5 minutes, take the reading. The overall changes, if you see, is a very nominal on the main picture, but if you go look at the variation of this, the peaks are quite good. The peaks are quite good. Some are a bit of random, but most are shifting more right. And as well as the peaks, conductance peak value is not higher, but shifting is bit of very evident from this curves. So it gives you idea, okay, the overall change within the concrete crushing is very noticeable. But failure is shifting left. Now if you see failure, this one is shifting left, which is a change in frequency or lowering the frequency, indicate the lowering the stiffness, which indicate the damage, the final fail. So this is quite being seen in the first 2 figure. The dotted one is shifting left, others are getting into a bit of right, but because there are local failure. But the fail is a global, the final fail is a global. The right shifting right, while for 4 mm, 8 mm, 12 mm, those strain control changes while we do test is a shifting right. This is the overall RMSD variation. The failure mechanism shown is very well. At least the clamp test and the metal wire test is good enough to see the changes through their sensing capacity, which is encouraging. Similarly, we see the change stiffness behavior. The stiffness behavior for a different baseline to the fail is decreasing more. which just gives the indication, yes, the damage that has happened being well controlled or well stabilized through the sensor reading. Now, we also do some RMSD variation based on the bond strength improvement. Now, what we see, both metal wire and clamp based has certain equivalent pattern or some or other pattern form as the sensor reading, as what is the mechanical reading from the bond strength, that is a pull-out test, and the RMSD is the sensor reading. So, sensor reading and conventional reading actually they go side by side for the clamp based and the metal wire based sensors, but for surface bonded we see bit of rampant change. Now, rather than to go back to the other part, this is a very smaller part I just covered. Now, we do speed of parametric study. What parametric we do? We change the cover to dia, that is cover to diameter, that is the diameter of the concrete specimen to the embedded length variations. We also do some variation as a corrosion form, accelerated corrosion form, and we do more testing in terms of conventional as well as piezo sensor based. So what you see is a Hobson potential method where we have to test how much corrosion happened, and we have to know how corrosion really altered the bond strength through the conventional test as well as sensor reading, and we also do Hobson potential method. Now, if you look at this, there is another first part. Maybe I'll just go. Okay, let me. 1 minute. This is the corrosion part which I am able to see. Now, this is how we see the corrosion. We do the Hobson potential method. So maximum with the 90 days of exposure, 80% of specimens goes for the most in corrosion form, in corroded form. We do see a variation of the exposure for in terms of compressive strength as a rebound power, bond strength as a pull-out test, and you see the how corrosion progresses across from 90 days of exposure for bond while it is being immersed in accelerated corrosion. So you see the rusting, discoloration, rusting you have started with the initially at the joint, surface joint between steel and concrete, then is the maximum deposition, then some cracks, and these are mostly the rust is completely deposited, and some of the crack also transmitted from the top to bottom, and some concrete is spanning out at the bottom. The completely corrosion we see, and if you see this particular signature is being taken because the exposure condition is so rapid. We don't take the intermediate strain control, we take the baseline and the final fail because we want to see if there is a change or not. So maximum for the surface bonded. Yes, sorry, this control one, if you see for 7 days, 30 days, 60 days, you have the baseline and at the failure load test, because we know 40 kilonewton is the maximum the failure load for pull-out test PD. And if you see for the surface bonded, we had for the sample 30 days, we see there is some wrong that happened in the surface bonded because it is completely corroded. But for metal wire and clamp test, the variation is very, very nominal. That means it gives you idea reusation, revamp, that is a reuse configuration, and non-bonded configuration is more important for such kind of interfacial bond strength monitoring, because anything that happened within the structure as a steel, it is rusted out. So in the 60 days, 30 days, we hardly get any kind of signal, but for those clamp based and wire based, we got a very nice one. So the other two are, first one A is for the surface bonded, then B is the clamp based, and the C is the metal wire. So if you see here B, C configurations for all the signatures, they are really performing well, and so is the RMSD variations. Now I got a bit of simple thought here. How to do a aggregate impact? So we do kind of aggregate variations. What is the aggregate packing in density effect into the overall question? Ultimately, concrete is maximum volume has crushed aggregates, right? 60 to 80% volume has aggregates. When they are not properly compacted, it usually what happens? It has more gap, voids and pores. So with the thought, we do some kind of change in sieve analysis by muting some of the size of aggregates. In gap graded, larger sizes gone. open graded smaller sizes are born, well graded all sizes are present, and uniformly graded we are with single size FDP. With the weighting variation of it, we do make some casted, some concrete cylinder casted, and we do some test in the pull-out test. If you see, this is not the one. Maybe I'll show you this. The fixed strength over here for the well strength, these are the strength, the total strength bearing capacity as well as the bond strength is higher compared to the other. The less is for single size variation, that is open graded 3.86, for the open graded, gap graded and well graded. Because of the confinedness of the aggregates by being compacted, then hardly change in bond strength. So the size variation in overall bond strength is very minimal, what I found. And which one is more elastic effect? All the three have more elastic effect, but the slip is maximum for single graded, because larger the motor content. A single size aggregate motor is more, you have a larger elastic behavior. But for the open, well graded and gap graded, the behavior is similar, and having the same system, it doesn't have much of impact. So let me show you the final one. How does also we take up strength variations? Both those surface bonded clad and metamed variations